Good afternoon. My name is Mike Kelly. I'm from Johns Hopkins Applied Physics Lab, and I'm very happy to be presenting the Compact Midwave Imaging System, which is a NASA IP16. So we are starting in our fourth year. So the first 3 years, we intended to develop the instrument and then do our airborne tests in the month of March here, which we just passed. And we too were impacted by COVID-19, so we did not get our airborne flights in yet. However, we're replanning that, and I'll show you the current status here today. I'd like to mention our team members, Arnie Goldberg and John Bolt from Johns Hopkins Applied Physics Lab, who are the engineers, Don Wu and Jim Carr, who are working on the software for the stereo calculations. Ivan Pacuso is doing the geometric calculations and the georegistration. And we've been working also now with Carol and Clayton for imaging scenes of interest for the planetary boundary layer. Next slide, please. So the basic problem that we want to address here are global winds and heights in the boundary layer. As discussed in the 2018 Earth Science Decadal Survey, precise, accurate winds are a very high priority. The objective of this project is to develop the capability to retrieve atmospheric motion vectors, and we want to do it at sufficient spatial and temporal resolution to study boundary layer processes such as diurnal variations or stratus to cumulus transitions in the tropics. Atmospheric motion vectors have been around for some time. They're a proxy for winds, and they're derived by tracking the motions of clouds, water vapor, dust, or other particulates using consecutive satellite images. And so we want to do this at high resolution, and also we want to work to reduce some of the limitations from the past. So we want to correct height assignment issues from atmospheric motion vectors that have come from the past that rely on infrared brightness temperatures or single satellite solutions. Infrared brightness temperatures tend to place clouds too low if they are thin or translucent or in the presence of temperature inversions. Single satellite methods that use stereo retrievals tend to have problems with an alarm track ambiguity, and that makes it difficult to separate cloud motions along the satellite track for cloud heights. So Jim Carr and others on our team have shown how to use imagery from two satellites to get viewing diversity from both low Earth orbiting or low Earth orbiting and geostationary to get the required the viewing diversity in order to be able to eliminate these errors. Next slide, please. So a way to compute accurate atmospheric motion vectors is shown on this slide. The basic idea is to fly leading and trailing CubeSats with midwave imagers to perform stereo calculations. The stereo methods presented there in the upper right-hand part of the slide. As a satellite moves forward from left to right, a push-beam imager can get a fore, a nadir, and an aft view, and that gives kind of an apparent parallax there that can be used to retrieve both the cloud height and the cloud motion. The trailing satellites used to correct the along track motions that provide the ambiguity that we referred to before. An imager that senses in the midwave, you notice we're talking about flying in the midwave there, between 3 and 5 microns is very useful for 24/7 retrievals because the clouds both reflect and emit in the midwave. And so the nighttime emissions will be used to get the nighttime motion vectors. And also the midwave is very useful for getting data down to the planetary boundary layer due to differences in emissivity. You see there estimated precision and geolocation accuracy and minimal detectable along-track cloud motion vectors, which are very good. Jim Carr showed in his 2018 paper using LEO geo retrievals that the precision and accuracy can be retrieved about these values. And we're hoping to show that we can do the same for a compact imager flown on a CubeSat, which will be a challenge. Next slide, please. So here's the CMIS instrument. We've integrated it. It was ready for our airborne test. It's an approximate size, about 10 centimeters by 10 centimeters by 18.5. So it's got the right volume. It has 3 bands at 2.25, 3.75, and 4.05 microns. 3.75 band is the primary one used for stereo imaging, and the 2.25 and 4.05 are the complementary bands used for temperature and removing the solar component. It has 3 components, 3 multi-angle components that you see down there in the table, and the weight and power are very good, less than 3 kilograms and 7 watts. And the operating temperature is 150 Kelvin, and we have a cooler to maintain that, which is a very modest temperature for an infrared focal plane array, and it has nearly telecentric optics. Next slide, please. So we have a stripe filter on it, a butcher block filter, and you see the design there on the right-hand side. We have 3 bands, the 3.75, the stereo imaging for the 4 nadir and view aft images, and then we have the 2.25 and 4.05 bands in between. We use a relatively spectrally wide band at 3.75 in order to be able to detect thin clouds, fog at night in the planetary boundary layer, and then we have the 4.05 band on the bottom right, and then 2.25 on the upper right. Band 3 has slightly expected performance that we're going to get here for the airborne version. As you see, they've slightly shifted from what we desired, but that can be corrected for a future spaceborne mission. Next slide, please. It has excellent sensitivity for polar and tropical PBL science. Well, as you know, infrared detectors get less sensitivity as it gets colder, and so the noise equivalent delta temperature is still about 1 Kelvin for the 3.75 micron band, and has excellent sensitivity as you get warmer there. So we expect that it can be used for both polar and tropical retrievals. The next slide, please. So what are the contributions to PBL science? So we see basically 3 examples there. Cold air outbreaks. You can look at the difference in the cellular structure. That's an example from MISR that we've calculated there. Tropical and subtropical clouds. You can look at the cloud bases and cloud tops. That's a very interesting methodology developed by Bohm et al. In 2018 for MISR. And then looking at the Arctic and Antarctic PBL. So we expect that we can retrieve the heights of the clouds directly rather than relying on infrared brightness temperatures that cause very large errors in the presence of large inversions. And being in the midway, we should be able to look at the variability in all seasons, including the polar night. So this is an excellent way to look at the planetary boundary layer across all regimes. Next slide, please. So our airborne test campaign is what we have coming up next. As I said, we were planning to do this in March of 2020. We're now scheduled in January of 2021. The basic idea is to retrieve atmospheric motion vectors, cloud top heights, cloud top temperatures, and sea surface temperatures using the bands that we've got on the CMIS. And the goal is to focus on the cloud top planetary boundary layer. We'll compare these with the Earth observing platforms such as Calypso, Aquaterra, and Surface Buoys, and we plan to apply racetrack patterns over these PBL regions so we can get successive passes and apply corrections. And then lastly, we want to demonstrate the engineering parameters, dynamic range, image quality, key registration. So we'll make 4 flights. The first one's an engineering flight, and the next 3 will be science flights under different conditions. So we can't wait to do this, and we're trying to get scheduled with Langley when they open back up. So thank you very much, and that concludes my talk.